Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. Today we are going to discuss about the module Signal to Noise Ratio from the paper Electronics. So students, let us see what we are going to learn in this module. First, we will discuss about the signal to noise ratio, that is its definition and significance. Second, the noise in the frequency domain will be discussed. Thirdly, various types of sources of noise will be discussed. Next, the one and only important factor in determining the signal to noise ratio, that is equivalent noise resistance, will also be discussed. Lastly, the noise factor. So students, and then we will also discuss about the amplifiers in cascade. How does the S by N propagates in this case? And then we will discuss how to enhance the signal to noise ratio which we want, which is our motive, using phase sensitive lock-in amplification. So students, let us start with a basic introduction about the module. The main characteristics of communication electronic systems is signal to noise ratio and bit error rate BER, which is defined via SNR. So as usual, SNR can be defined as signal power to noise power ratio. This approach is developed in many works. For example, contains a description of using of multiple linear regression with coefficients chosen for different types of noise for defining of SNR. So estimation of signal to noise ratio SNR can be made via relation between autocorrelation functions of a signal and noise shifted by time. But noise and signal levels, they have arbitrary chosen values. Effective SNR estimation, defined as the difference between standard SNR and signal quality SNR, is used in many areas of science and engineering, such as in wireless telecommunication systems, medicine, nuclear physics, neuroscience, sound technique, optoelectronics, nanotechnology, astrophysics, etc. Signal to noise ratio. The relative magnitude of noise voltage is defined as S by N equal to the average value of the signal in volts divided by the RMS value of fluctuations. So in decibels, the power ratio, that is S by N in decibels, is equal to 10 log of signal power divided by the noise power. So our aim is to increase the S by N ratio so that the detectability of the signal is increased. Amplification is not useful because noise is amplified by the same factor as the signal. That is, we have to distinguish the signal from the noise. Noise may be contributed by each stage of a measurement system. The noise voltage contributed by each stage is given by noise figure F is equal to S by N input divided by S by N output. So, when F is equal to 1, that is, there is no noise contributed by the stage, F greater than 1 for all the systems, and F is 1.3 for many semiconductor devices. Let us now discuss the noise in the frequency domain. The average value of time varying noise is constant as slowly varying with time dc, while noise has a complex waveform. So these differences are most conveniently described by the frequency spectrum. Fourier transform is an efficient tool to convert an amplitude variation as a function of time ft to a complex amplitude and phase spectrum as a function of frequency capital F omega. So capital F omega is equal to the integral from minus infinity to plus infinity ft exponential minus j omega t dt. So some of the important Fourier transform of technical importance are shown in this figure. The importance of frequency domain is that it can describe the frequency bandwidth in which the signal information is carried and distinguish this from the frequency bandwidth over which the noise exists. For example, as shown in this figure, this waveform can be analyzed in frequency domain as having two components, one defining the signal and the other defining the noise. Because signal is likely to be well defined in time, the frequency spectrum which contains the signal information is relatively limited in width as compared to the noise spectrum. Hence, the instruments are built with a specific frequency bandwidth delta f so that all frequency components of a signal falling within the measurement bandwidth will be detected, all those outside will not be observed. So signal to noise ratio SNR must therefore be calculated taking into account the frequency bandwidth of the measurement system. The equivalent bandwidth of a pulse of duration t is f0 equal to 1 by 2t. Let us now discuss the different sources of noise. First one is due to inherent fluctuations. Some experimental systems are inherently unstable and they lead to measurements which fluctuate with time. This inherent noise has to be treated statistically or by noting the variation over the periods of time. For example, optical fluctuations in starlight, bad electrical contacts, semiconductor, etc. The second type of noise is thermal or Johnson noise. The density of electron gas in a resistance R fluctuates spatially, leading to the variations in potential difference V0 between the contacts. So the variations arise because of the thermal motion of the electron gas, and possible frequencies are unlimited. This is termed as the thermal or Johnson or white noise. Thermal energy available at temperature T is approximately kT. So this energy is spread across the entire frequency spectrum. So if the measurement system has a limited bandwidth delta F, as shown in this figure, only a fraction of the energy will be measured. So the noise power available to a measurement system of frequency bandwidth delta F will be kT delta F. The resistor may be treated as a perfect noiseless resistance R in series with an internal voltage source Vn. The maximum power that can be transferred to an external load resistance Re occurs when Re is capital R. So the terminal voltage is then V0 equal to Vn by 2. So the noise power will be kT delta F is equal to V0 square by Re equal to Vn square by 4R. So this RMS noise voltage Vn is equal to root of 4 kTr delta F. So Johnson noise exists in all the resistive circuits. It cannot be eliminated, but its effects can be reduced. The next type of noise is a short noise. This occurs due to the collection of electrons at an electrode or by diversion over a barrier. So consider capital N number of charges having charge Q collected in time capital T as shown in this figure. So the mean current will be I0 equal to Qn by capital T. Since this is a random process, there will be a statistical uncertainty of plus minus root n in the number of charges collected in this time. That is, capital I is equal to I0 plus IRMS, and the ratio IRMS by I0 equal to root n by n equal to 1 by root n is equal to 1 by I0 t by q to the power half. So this figure shows the frequency spectrum of the short noise. The next type of noise is 1 by f noise. Many system shows more noise power at lower frequency than predicted by thermodynamics. So excess noise due to unknown effects at the surfaces, contact barriers, and improve with device design. This noise is associated with the generation and recombination of minority carriers in semiconductors. Let us now discuss about the quantization noise. It occurs due to analog to digital conversion observed in digital instruments like multimeter, picometer, etc. High frequency or transit time noise. Let us discuss about it. In semiconducting devices, when the transit time of carriers crossing a junction is comparable with the periodic time of the signal, some of the carriers may diffuse back to the source or the emitter. Next is generation recombination noise. In semiconductor devices, some impurity centers will be ionized on a random basis. So being energized thermally, thus, or random generation of carriers occurs in these devices. Also, the carriers, they can recombine with ionized impurity centers on a random basis, either directly or through trapping centers. So the result is that the conductivity of the semiconductor has a random components giving rise to noise current. Let us now discuss about the contribution due to multiple noise sources. Now, if there are several noise sources contributing to the total noise power, then the noise power total is equal to noise power due to 1 plus NP2 plus NP3 and so on. So, in terms of RMS voltage contribution, Vn square total equal to Vn square 1 plus Vn square 2 plus Vn square 3 and so on. So, equivalent to the quadratic addition of standard deviations in error analysis. Equivalent noise resistance. The noise originating in a device, it may be active or passive, can be represented by means of a fictitious resistance Rn. So assuming Rn to generate the noise at room temperature, the actual device which is being assumed noiseless. So as shown in the figure A above, which shows an amplifier with an input resistance Ri and equivalent noise resistance Rn. Noise resistance should be a part of manufacturer's data for the device given for specific operating condition. Equivalent mean square noise voltage Vn0 square appearing due to Rn is 4 Rn kT delta F. Figure B over here shows the equivalent mean square noise voltage Vn square, which is appearing at the input terminal of the amplifier, that is Vn square equal to 4 multiplied by Ri plus Rn kT delta F. In effect, the amplifier noise is referred to the input circuit so that the amplifier be assumed as noiseless. Now students, note over here that Rn is a fictitious resistance which does not affect the real resistance at the input. So here input resistance remains at Ri even though the effective resistance from the point of view of noise generation is Ri plus Rn. Here Rn is not involved in the reduction resistance. So in general, for Thevenin equivalent circuit, the signal to noise power ratio of the system is S by N equal to Vs square by 4 multiplied by Rp plus Rn kT delta F. Let us now discuss about the noise factor. The noise factor F of an amplifier may be defined as F is equal to S by N power ratio at the input divided by S by N power ratio at the output. That is, it is equal to PSI by PNI multiplied by PNO divided by PSO, where PSI is the signal power available at the input, PNI is the noise power available at the input, PSO is the signal power available at the output, PNO is the noise power available at the output. So the temperature of the input source is defined as the room temperature. S by N at the output is less than S by N at the input because amplifier or network will add noise, that is F greater than 1. So the available power gain G is G equal to PSO by PSI, which implies F equal to PNO by G PNI, or F multiplied by G multiplied by PNI, and PNI equal to KT delta F. Thus, PNO equal to FG KT delta F. This is the output noise power, which is increased by the factor F. Let us now discuss about the noise factor F in terms of Rn. The output S by N equal to Vn square divided by 4 multiplied by Rp plus Rn Kt delta F. Because both the signal and the noise, they will be amplified by the same amount, and noise of amplifier is taken into account by Rn. We know that the available input S by N is S by N input equal to Vs square by 4 Rp Kt delta F. Therefore, capital F will be equal to S by N input divided by S by N output, which is equal to Rp plus Rn divided by Rn. So the F can be expressed in decibels, which is known as the noise figure. So noise figure equal to F decibels equal to 10 log 10 of F. That is, consider a case where Rn is 0, so F will be equal to 1, which implies that F in decibels will be equal to 0 decibels. So amplifier input noise in terms of F, let us discuss that. The total noise referred to the input can be represented by PNO by G as PNI total equal to FKT delta F. The source contributes KT delta F of this. Therefore, the amplifier must contribute PNA, where PNA equal to FKT delta F minus KT delta F. Amplifiers in cascade. In the above figure, the noise input to the amplifier 1 is F1 KT delta F, and therefore the noise input to the amplifier 2 is G1 times this plus the contribution from amplifier 2 itself. So noise input to the amplifier 2 is equal to G1 F1 KT delta F plus F2 minus 1 KT delta F. So the output noise power, which is that from amplifier 2, is G2 times the input noise power to the amplifier 2. So we can write PNO equal to G1 G2 F1 KT delta F plus G2 F2 minus 1 KT delta F. The overall gain is G equal to G1 G2, so that the overall noise factor is capital F equal to PNO by G1 G2 PNI, which is equal to, putting the value of PNO over here and PNI, G2 G1 F1 KT delta F plus G2 multiplied by F2 minus 1 multiplied by KT delta F divided by G2 G1 F1 KT delta F. So we can write F equal to F1 plus F2 minus 1 by G1. So the argument can be extended for additional amplifiers as F equal to F1 plus F2 minus 1 by G1 plus F3 minus 1 by G1 G2 plus so on. This is known as Friis formula, and here G is the power ratio. Signal to noise enhancement, and this is done by phase sensitive lock-in amplification. Now here a switch allows the signal to pass to some form of averaging circuit, either directly positive or via an inverting amplifier negative. Switch is driven by an AC voltage at frequency F, and its position is denoted by the polarity shown. So the averaging circuit produces a time average of the waveform existing at the output of the switch. So the waveforms shown in this figure existing in the circuit at different parts of the AC cycle under various circumstances are given below. First, if the switch frequency and the signal frequency are identical and the two waveforms are in phase, the negative going parts of the signal waveform are inverted and the output of the averager is positive and finite. Second, if the switch frequency and the signal frequency are identical, but the two waveforms are 90° out of phase, the output of the switch is a complex AC waveform equally spaced about the origin. The output of the average is 0. So students, let us summarize what we have learned in this module. Firstly, we discussed about the signal to noise ratio, that is its definition and its significance. Secondly, the noise in the frequency domain was discussed. Thirdly, various types of noises, that is inherent fluctuations, thermal or Johnson noise, short noise, 1/f noise, quantization noise, high frequency or transit time noise, generation recombination noise, they were all discussed in this module. Next, we discussed about the contribution of the equivalent noise resistance. Then another important parameter, that is noise factor, was discussed, and how the S by N ratio propagates when the amplifiers in cascade configuration, it was also discussed. Lastly, How to enhance the signal to noise ratio using phase sensitive lock-in amplification was also discussed in this module. Thank you.